Hey guys, this is Dr. Calkins again. Today we're at experiment 14, page 93. We're going to look at intermolecular forces with transition metals. So this is kind of a hybrid force where we have positive metal cations attracting our partially negative atoms. So we have two things going on today. We have a stationary phase, which is the phase that stays there, and then the mobile phase that moves. In order to make that mobile phase, which I've done for you already, we have to mix acetone, which is a ketone. Notice here's that key-like ketone feature. We're going to mix it with hydrochloric acid, very nasty, save you that smell, and water. As we mix those together, we're going to notice that very quickly it reacts to form what looks like a double alcohol. There's a fancier name for it called an acetal, but we don't learn that in this class. But to us it looks like a random OH kind of alcohol group. And you can imagine that much like these very electronegative atoms, these oxygens feel very negative, and as they do, those electronegative atoms are going to attract transition metal cations. And what's unique about that is transition metal cations can be different sizes. So depending on how well they attract oxygen through this ion to dipole attraction, based on size and based on attraction, that's going to allow this molecule to pull them up that stationary phase, paper in our case, and see how far they can race. So as we get ready for lab, one of the first things we have to do is prepare our racetrack. So in order to do this, we have to make our chromatography paper look like this paper. We're using unknown letter P, so you can mark that down. And to do this, we're going to have to measure up 2 centimeters on both sides, make a mark, connect that mark across with a horizontal line, roughly evenly space across 6 little hash marks, label them from the manganese ion, the iron ion, the cobalt ion, the nickel ion, copper ion, and the unknown, which contains 2 of those previous 5. And then once we soak those to the paper, they can race up the racetrack. And based on who attracts that motorcycle-like molecule on the front page, they're going to race up the paper, and depending on who has the best attraction, they're going to race the farthest. And in this case, somebody might actually win. So let's take a minute to create this diagram. We're going to take this paper and this ruler and draw it out. So poof, we're ready to go. We have manganese, iron, cobalt, nickel, copper, and unknown P, which is going to have 2 of those. As you look at our data sheet, one of the first things we're going to have to worry about is the original spot color. So as we get to that page 95, again, unknown letter P, we're going to have to record those colors before we put it in the developing chamber and let it soak for 45 minutes. So let's go do that. All right, so we're going to dot these papers in order for those little cross marks. So starting with manganese, these capillaries hold some fluid. We're going to put it on the crosshair a couple times, let it soak. As we're doing this, feel free to record the colors that you see. Got lucky on that one. And lastly, our unknown. Guys, 2 of those 5 to have to deal with. So I've stapled my paper into a cylinder. Notice I didn't allow it to overlap because that would give it double the absorbency and those would cheat in their race. Also, we had the staple at the top because we're going to soak this in hydrochloric acid, which would eat the staple. Here's our liquid phase. This is our little motorcycle-like molecules that these transition metal ions are going to ride in, and we're going to let them soak for 45 minutes and see who wins the race. So notice you can see already the ions are getting soaked up the paper, and as we get closer and closer, they're going to start pushing off that start line up towards this new finish line in 45 minutes. So see you then. All right, so 45 minutes, poof, went by, And looky there. Our spots have raced up the paper. Some didn't make it, kind of like me in a race. Although some did make it, so maybe when I race my daughter, I try a little harder. But now we need to dry this mobile phase off the paper. It's very corrosive now, so I'm wearing my gloves. Also smells terrible, so let's go take it to the oven. So we're going to put it in the oven for about 5 minutes, but much like brownies, if you leave them in too long, it's going to burn, so we don't want that to happen. So see you in 5 minutes. Poof, 5 minutes went by. So now let's record our colors. So as we look at this, we're going to fill out the developed dry colors. We did the original spots before they went into the solution. So now we're filling out this row for each of our ions. So as we look, manganese disappeared. So we've got to deal with that with some testing solutions later. Iron definitely winning the race, way up there high, that yellowish color. As we go to cobalt, notice it made it pretty much up the paper with blue color. Nickel kind of vanished, although it shows a little bit of a trace of a color. And then copper has this kind of slightly greenish yellow color with a little bit of blue. The unknown does show one of two already. Notice the top one yellow starts to give us a good match of the iron that we saw earlier. So now we have half of our unknown figured out. We just need to find the one that's missing. All right, so our paper is super acidic still. The hydrochloric acid is now dried on there, what's left of it anyway. So we're going to have to neutralize it. Ammonia is a base. It's a amine-like molecule, or RNH2 group. This one just has 3 hydrogens. So we're going to neutralize the acid on the paper by putting it in. And notice when we do this, lots of smoke. That smoke is ammonium chloride formed from the ammonia and hydrogen chloride molecules reacting together to make that white dust. We're going to let it go until that smoke stops. So we're going to check it to see if there's still smoke, and way too much smoke, so let's wait a little bit longer. All right, so let's check it for smoke one more time. Looks like there's a little bit, but probably good enough. So let's check our colors. And now we can unwrap it. So I'll give you a few minutes to notice any color changes. Notice not a whole lot has changed, but the paper is now a little safer to touch. We did get a little prettier version of copper. Also notice nickel is trying to show up. That's what told me it was probably just about ready. And then manganese still missing. So now we need some separate chemical tests for them. So again, at this stage, we're looking for that neutralized color because we neutralized it with the ammonia chamber and the fume hood. So we can take those colors down. But do notice the next step, we need sodium hydroxide treatment with our manganese, and we need the dimethylglycine treatment with our nickel, and we have that right over here. So in our case here, nickel, we're going to treat it with sodium hydroxide, which is just a stronger base. It's going to react enough to produce a color change, and this is what we'll record. So we're just streaking up and down with a Q-tip, and notice as we do, we start to magically see manganese start to show up. Now that we know where manganese was hiding out, we're going to go over to the unknown and see if it's hiding out, because we already know that that match up top is there, but we have one of these two that are missing. And as we streak, we don't see anything yet. But we do see manganese as this dark brown turd-like color. So next is our last test of the DMG. So let's do that on our nickel. Notice it's kind of showing, but not very well. This is definitely going to brighten it up. This one Crayola makes a lot of money off of, so don't tell them they were using it in class. And notice here, very pretty pink color. Only showed up with our DMG solution. As we go over to our unknown to see if, again, we have one hiding, and sure enough, our pink color is starting to appear. So now we have our second identity to our unknown. So at this point, the lab should be completed on this page. Again, unknown P is going to have 2 answers in it now that we've matched up. Very similar. we're going to calculate how they finish the race. So little d is the distance that the spot travels to the center, and big D is the distance to the top of the actual race line, or our mobile phase line. So as we look at ours, I had made a pencil mark when I took it out. I just didn't show it earlier. So that pencil line tells us our finish line. So for each spot, we're going to measure in centimeters to the middle, and then divide it by top number, middle divided by the top number, although that one finished. So it's going to be 1, middle divided by the top number, middle divided by the top number, middle divided by the top number, and then here we're going to do it twice because we have two different spots, all divided by that top number, and I'll do that for you now. All right, so as you can see, manganese traveled about halfway, so about 0.55 to the center of its spot. Iron, actually second, traveled all the way up, so 1.0. Cobalt traveled about halfway again, or about 2/3 way, 0.67. Nickel about halfway, 0.48. Copper about 3/4 of the way, 0.79. And then we have that 1.0 for the iron match, and then that 0.48 for the nickel match. So all that remains is a couple questions that we'll go over here in a second. So as we look at these questions, question number 1 was really answered on the front page. Transition metal cations are positive ions, and oxygen atoms are very electronegative. So that attraction is what made the race work, and that attraction is what allowed some atoms to win and some to lose, and that's questions 2 and 3. Question 2 said who won the race. That would be definitely the highest number that we calculated a moment ago. And then who lost was definitely the one that traveled the least distance. Sometimes manganese and nickel kind of trade places here, but both of those, in this case, are going to be some of the lower ones. And that's it for this lab.